So now we're going to talk about the last part of this limits at infinity and asymptotes, which is drawing graphs of functions. And so I'm going to just give you my disclaimer. I think it's going to be a long section. I have many pages of notes here. Hope it's not going to be too dry. But I really want to go through the process several times to show you how it works. We're going to see right down here, there's a multi-step process, 6 steps to come up with the information you need to effectively draw the graph. So learning outcomes for this: analyze a function and its derivatives to draw its graph. And we're going to do a pretty thorough analysis. So our steps to do that are as follows. There we go. Let's see here. Given the function f, use the following steps to sketch the graph of f. Determine the domain of the function. Locate the x and y intercepts. Put in 0 for y to get the x-intercepts, 0 for x to get the y-intercepts. Evaluate the limits of f of x as x approaches infinity and as x approaches negative infinity to determine the end behavior. If either of these limits is a finite number, L, then y equals L is a horizontal asymptote. If either of these limits is infinity or negative infinity, determine whether f has an oblique asymptote. Determine. If f is a rational function, such as f of x equals p of x over q of x, where the degree of the numerator is greater than the degree of the denominator, then f can be written as f of x equals p of x over q of x equals g of x plus r of x over q of x. And where the degree of r of x is less than the degree of q of x. So you probably heard me saying this if you watch the other videos. This is just the long division, something you learned back in your pre-calculus days. The values of f of x approach the values of g of x as x approaches positive or negative infinity. If g of x is a linear function, it is known as an oblique asymptote. Also, the book is called a slant asymptote. Determine whether f has any vertical asymptotes. Calculate f prime, find all critical points, and determine the intervals where f is increasing and where f is decreasing. Determine whether f has any local extrema. Then do the second derivative. We use that to find concavity. So determine the intervals where f is concave up and where f is concave down. Use this information to determine whether f has any inflection points. So the inflection points, if they exist, would occur where x is 0. F prime of x is 0. F double prime of x is 0. Oh, if I could speak today, it'd be great. The second derivative can also be used as an alternative means to determine or verify that f has a local extrema at a critical point. So remember, if its second derivative is positive for an extrema that you found a critical number from the first derivative, then it's concave up, and that's a local minimum. If it is negative, then it's concave down, that's a local maximum. Okay, so here's our first one. See a nice little space here. We're going to take a lot of space to work this problem, so just be patient with me. It's a bit of a process. So once it's to sketch the graph, and I found it easy to expand this and to say, okay, f of x, if I multiply this out, I'm not going to go through the whole thing, but it's x cubed minus 3x plus 2. Okay, and so our step 1, it's a polynomial, so it's going to be defined everywhere. Okay, let's see step 2. We're going to find the intercepts. So y-intercept is where x is 0. So our f of 0 is 2. So y-intercept is 0, 2. X-intercept is where you set it equal to 0. It's at f of x equals 0. So x cubed minus 3x plus 2 equals 0. And it's actually, I think, easier in this case instead of you doing it that way, instead of going back and trying to factor. We already have it in factored form, so we can say we're x minus 1 squared times x plus 2 equals 0. So x minus 1 is 0 is where x equals 1. X plus 2 is 0 where x equals negative 2. Okay. Now, by the way, the x minus 1 being a 0, it's a double root, so it's multiplicity 2, so that makes me think it's going to be, it's going to bounce at that point. Okay, it won't cross through. Next step, step 3. Oh, I can't write there. Step 3, we have evaluate the end behavior. So we take the limit as x goes to infinity of this function f of x, and that's going to be infinity. And then we look at the limit as x goes to negative infinity of this function f of x, and that's going to be negative infinity. And I think we can see that because as x gets big, it's going to get big. As x gets small, it's going to get really small. Okay, step 4. Any vertical asymptotes? The answer is no, because it's a polynomial. Just cross the line on that one. Step 5, now we start getting into our calculus skills. So all this up to this point you could do from your pre-calculus skills. We're going to take the derivative, so the f prime of x. Let me just remind, well, you can see right out there on the screen. Our f of x is x cubed minus 3x plus 2, so the first derivative is 3x squared minus 3. So I'm going to take that and set it equal to 0 to get my critical points. 3x squared minus 3 equals 0. So that's 3 times x squared minus 1 is 0. So that means that x minus 1 is 0, so x equals 1. X plus 1 is 0, so x equals negative 1. And let's look at a graph here, or a chart here. So I know these critical values are at negative 1 and 1. And this is in reference to the first derivative because we're going to try to find, is there a behavior that has to do with the slope? So where's increasing and decreasing essentially? So which intervals? I mean, so we have these intervals from negative infinity to negative 1, from 1 to negative 1 to 1, and then 1 to infinity. So you can see all that. Those are the intervals. So I think I can still write this far over. So our test values would be like negative 2, 0, and 2. And what we're looking at here would be 3 times x minus 1 and then x plus 1. You really don't need the 3. It's just a constant. But if it had been a negative, we'd have to consider that, how that's affecting these values. So let's put this negative 2 in here. Negative 2 minus 1 is times 3 is a negative. Negative 2 plus 1 is a negative. So the result is a positive. That means it's an increasing slope. And then put a 0 in here. That's going to be a negative for the first one, a positive for the second one. So it's negative. That's a downward slope. And put the 2 in there. So it's positive, positive, and positive. So it's an increasing slope. That means that x equals negative 1 has a local max. And x equals negative or positive 1 has a local minimum. Okay, we're not finished yet. Now we need to talk about step 6. We have a second derivative. So our first derivative, just to remind you, I'll leave it on the screen there. So we're looking at the second derivative of x is 6x. So 6x equals 0 when x equals 0. So if there's an inflection point, that's where it's going to be. And let's see if there is an inflection point. That occurs when we have a change in the concavity. So if we have x being 0, we could try -1 and 1. Those are some test values. And 6x is here. So if I put -1 in there, that's negative. Put a +1, it's positive. So that means this is concave down. And then concave up. That means from -infinity to 0, it's concave down, and from 0 to infinity, it's concave up. And if we go back into the original function, we have some values to come up with. We need to find this f of -1, because that's going to be a local maximum, f of 0, and f of 1. And let's see, our f of 0 is 2. That's not hard to come up with. Our f of -1 is, I believe, 4. And our f of 1 is a 0. So that's one of our intercepts. So let's go ahead and try to graph this thing based off the information we have. We know that 2 was an intercept. To 0, we know that 0, 2 is an intercept. And we know that 1 is an intercept. And so it's going to be coming up. It's going to peak here at 1, 4. It's going to come up, peak at 1, 4. In fact, why don't I change the color of this to red? It's going to come up, peak there, and come down, and then it's going to bounce and go back up again, because that's a local minimum. So it looks roughly like that. Local max, local minimum. And we can see at this point here, that's our inflection point. And it changes concavity. So it goes from being concave down to concave up. My graph may not be perfect, by the way, so it probably should be more like a better curve like that. Okay, hope that helps. Let's go ahead. We've got a few more of these to do. Sketch the graph of f of x equals x minus 1 cubed times x plus 2. So I did a lot of side work on this one. So I'm gonna, I guess, start it right up here because we really need the space to work on these problems. Okay, so what we have is x minus 1 cubed times x plus 2, and that comes out to be just expanding that, comes out to be x to the 4th minus x cubed minus 3x squared plus 5x minus 2. Okay, so step 1. We let's say look for the domain. Domain is all reals because it's a polynomial. Okay, step 2. We're going to find the intercepts. Okay, so the y-intercept is at x equals 0, so f of 0 equals -2. You can see that there. So y-intercept is at 0, -2. Okay. X-intercept, I'll go back to the factored form of this. And the factored form had x minus 1 cubed and x plus 2. So x minus 1 equals 0, so x equals 1. And x plus 2 equals 0, so x equals 2. So at 1, 0, that should be -2. And -2, 0 should be our intercepts, x-intercepts. Okay, step 3 in behavior. Well, this is a polynomial with the leading coefficient being positive. So it makes sense then that the limit, being a polynomial, as x goes to infinity of f of x is going to be infinity. And the limit as x goes to -infinity of f of x equals -infinity. No, I have to take it back. They're both positive because it's a quartic. Okay, so they're both positive. Sorry about that. Good thing I look at my notes. And then step 4, it wants us to look for vertical asymptotes or no vertical asymptotes. So none of those. Step 5, we get into our calculus part, we take the derivative. So our first derivative, f prime of x, is going to be so I did this actually 2 different ways. And from the polynomial perspective, that's 4x squared, x cubed, minus 3x squared, minus 6x, plus 5. And that's not a big surprise from what you saw up here. I mean, just bringing those powers down and subtracting 1. Getting the zeros was a little bit of work. I'm not going to go through all that because that's not really the level of this course. But the other derivative of this, if you would look at this, if I hadn't multiplied it out, in a factored form, it would have been an x minus 1 squared times 4x plus 5. So this tells us that the critical numbers, if you set those equal to 0, critical numbers are x equals 1 and -4/5. -5/4, excuse me. So with that, I would look at a chart here. Just keep going sideways. So that means we would have something like -4/5 and 1. And our factors would be x minus 1 squared, and then the 4x plus 5. And picking something smaller like -1, between them like 0, and bigger than 1 like 2. Plugging them in. Oh, it's 5/4, not 4/5, so I've got to fix that. -5/4, and this would be -2. Okay. Putting a -2 in here, it's going to square out the negative, so that's positive. But putting a -2 down there, it's a negative, so it's a negative. That means our slope is downward. Putting 0 in, we're going to end up with still a positive and then a positive. So that's going to be a positive, so it's the upward slope. Putting the 2 in there, we're going to have a positive and a positive, so it's a positive, again, an upward slope. So the only thing we're going to see here is that at this point here, we'd have a local minimum at x equals -5/4. And that f of -5/4, I put in the calculator, I got -8.54. Okay. And our next step, I'll just keep sliding. I don't know how far I can go. Feels like I'm getting close. Yeah, there's the edge. Okay. Step 6, we want to check for concavities. We're looking for second derivative. Our second derivative that I came up with was 12x squared minus 6x plus, or just minus 6, not a plus 6. And I spent the time factoring this. It comes out to be a 6 times 2x plus 1 times x minus 1. And then, so 2x plus 1 equals 0. So x equals -1/2. X minus 1 equals 0, so x equals 1. And that's where we would likely have inflection points, but let's check that. That's where we have it, if we have a change in concavity. So -1/2, and then +1. And we'll use these factors. That's 6 times 2x plus 1. Then, oh, don't need that line there. And then we have the x minus 1. So if I put a smaller number like -1, and then we could do a 0 and then 2, we would have a negative here, and a negative here, which gives us a positive. That means it's concave up. Put into 0. We're going to have a positive here, a negative here, so it's a negative. So concave up, concave down. And then put in the 2, we're going to have a positive and a positive, so it's positive, so it's concave up. There's so much to consider here. It's like so many details, and it's easy to kind of get a little lost in it. Okay, so what does this mean? Our f of -1/2 is going to be equal to -5.063. And that's an inflection point. So these are the inflection points. And we know that because these are places where the concavity changed. Then f of 1 is going to be 0. Okay, I think we have the information we need to put this together. So I'm going to slide up here a little bit. So if you need that, you can pause it. I saved some space over here to do the graphing. Hopefully it's enough space. Maybe let's just do it over here. I think I got more space right here. Okay, so putting together the graph. I need a lot of downward space. Maybe I'll get rid of this. Put it up here more. Okay, so I said at 1, 0, we have something going on. We also have something over at -2, 0. And we had something at 0, -2. And then we had our only local extrema was down here at, so -1, -8.5-ish, something down. 2, 3, 4, 5, 6, 7, 8, 9. So something right about here. So this is coming down. It's nice if I could draw I'm trying to draw a curve, but not a squiggly curve. And it comes up, turns here, and then goes Sorry, it comes up like this and goes up like that. I lost the whole thing, okay. There, okay. There's our graph. I want to point out the inflection points. So they occurred at x equals -1/2, so somewhere down in this area, it changed its inflection. It's a concavity, I should say. And then somewhere around 1, it changed concavity again. I should have done red. Okay. Cool. Cool, cool, cool. Who knows that reference? Leave it in the comment. Okay. So it's concave up, then concave down for that little bit, and then concave up again. Okay, let's go on to the next one, which was right below it in green. No, this was the green one. Right below it in, oh, look, we did have more space down here. Sketch the graph of f of x equals x squared over 1 minus x squared. So now we have a situation with a vertical asymptote because we have a rational function. Okay. So I'm going to come up here and utilize as much space as I have. And what we have is f of x equals x squared over x minus 1. Isn't that right? X squared over 1 minus x squared. Okay. For this one, the domain is going to be a little more complicated, so let's look at our step 1. Domain is going to be all reals except the denominator, so we have that 1 minus x squared equals 0, so x squared equals 1, and x equals plus or minus 1. These are the places it's not defined. So the domain is -infinity to -1, 1 to 1, -1 to 1, and then 1 to infinity. Okay. Next step is the intercepts. So the x-intercept occurs when y is 0. So we take that numerator, set it equal to 0. That's where x equals 0. But the y-intercept also occurs when x is 0. So you put 0, f of 0, well, I'm not even going to say that. If you put 0 in place of the x and the x squared, you get 0. So there's only one intercept at 0, 0. Okay, step 3 is in behavior. So we'll look at the limit as x approaches 1 from the right side of our x squared over 1 minus x squared. And we get -infinity. No, I skipped a step. Sorry. That's the next part. In behavior, we look at the limit as x approaches positive or -infinity. And given that it's squared in the numerator and denominator, the x term is squared, so any negative squares out. So that makes it the positive or negative going to be the same. So 1 minus x squared. That's going to be the limit as x approaches positive or -infinity of, if I divide everything by x squared, I have 1 over x squared minus 1. So I hope that clarifies it. You end up with just -1 as your limit. So we have a horizontal asymptote at x equals y equals -1. Okay, next one is step 4. And then in step 4, we find vertical asymptotes And I know you're already probably saying to me through the screen, oh, it's clear where they are. That's where the denominator is 0. Oh, let's do this one more step. X squared minus 1 is 0, so x squared equals 1, or x equals plus or minus 1. So here's where we're going to look at the behavior of the graph as we approach those asymptotes. So we'll look at the limit as x approaches 1 from the right side of this function, x squared over 1 minus x squared. And that's going to be negative infinity. We look at the limit as x approaches 1 from the left side of x squared over 1 minus x squared, and that's going to be positive infinity. We look at the limit as x approaches negative 1 from the right side of x squared over 1 minus x squared. That's going to be positive infinity. And we look at the limit as x approaches negative 1 from the left side of x squared over 1 minus x squared, and that's going to be negative infinity. Okay, so that helps when we go to graph it. Okay, we have step 5. Step 5 says, oh, we've got to do the first derivative, so we're going to find critical points. So f prime of x is going to be 2x over 1 minus x squared, x squared, and that quantity is squared. So with that, our critical numbers are going to be x equals 0 from the numerator, negative 1 from the denominator, and 1 from the denominator. So I'll make a little chart here. Negative 1, 0, and 1. And then I have the values of the components, 2x, and then 1 minus x squared squared. So given that the last term is squared, anything is going to come out positive. Okay, so this is going to be, let's try like a negative 2, a negative 1/2, a 1/2, and a 2. So we end up with a negative and a positive. Like I said, this last row is going to be positive always. Put a negative 1/2 in, you're going to get a negative for that first one. Put a positive 1/2, you get a positive, and a positive 2 gives you a positive. So this is negative, negative, positive, positive. That means the downward slope, then it goes upward slope, upward slope. This means that you have a relative minimum at x equals 0, and we already know from above that that point is at 0, 0. Okay, that's good to know. And let's go on to step 6. Step 6 says we get the second derivative, f double prime of x. So we're looking for concavity. And that's going to be 6x squared plus 2 over 1 minus x squared cubed. And our numerator, that's 6x squared plus 2 equals 0. That's 6x squared equals negative 2, or x squared equals basically negative 1/3. That's not possible. So your 1 minus x squared from the denominator is where you're going to find your potential plus or minus 1 inflection points. So we look at this in the chart. Negative 1 and 1. And we have our 6x squared plus 2, and then our 1 minus x squared cubed. So from the numerator, that's always going to be positive no matter what we choose for test values. So I'm going to try negative 2, 0, and 2. Down below, though, because it's a cubed outside of this 1 minus x squared, it's a cubed, it can be negative. So if what's inside is negative, it'll be negative. So if you put the negative 2 in there, that will be negative. Put the 0 in there, it'll be positive. Put the 2, it'll be negative. So we end up with a negative, a positive, and a negative. So this is concave down, concave up, and concave down. So let's go ahead and graph this. And at -1 we have an asymptote, +1 we have an asymptote, and then we have at 1 here we have the asymptote. We'll do those in green. Okay, so our graph looks like this. It's going to come down to, oh, let's go to red. And then these are going down as they approach. And that's it. Okay, got another one to do here. Okay, we have another example here. And we're going to sketch the graph of this rational function f of x equals 3x plus 5 over 8 plus 4x. And I'm just going to rewrite this. I don't know why they wrote it like this. I prefer blue, thank you very much. That'd be 3x plus 5 over 4x plus 8. And so, first of all, the domain, let me go through my steps. Step 1, the domain is all reals except except 4x plus 8, set that equal to 0. 4x equals 8, negative 8. So x equals -2. So it's going to be -infinity to -2 union -2 to infinity. So we have to exclude the -2 because it makes the denominator 0. Our step 2 is to find the intercepts. So the y-intercept occurs when x is 0. So f of 0 is going to be 3 times 0 plus 5 over 4 times 0 plus 8. So that's going to be 5/8. So that's going to be at 0, 5/8. And the x-intercept occurs when y equals 0. So we just set the numerator equal to 0. So 3x plus 5 equals 0. 3x equals -5. X is -5/3. So that's at -5/3, comma 0. We use that when we go to graph it. Step 3 is the limits. So step 3, the end behavior limits. Limit as x goes to positive or negative infinity. It's going to be the same in this case. So we have 3x plus 5 over 4x plus 8. And if you remember the rules we talked about before and that you learned in pre-calculus, they're the same degree, so it's just going to be that 3 over 4. Step 4 is the vertical asymptotes. So we already saw what that's going to be. So vertical asymptotes, that's going to be where the denominator is 0. So 4x plus 8 equals 0, or x equals -2. Let's go to step 5. So this is going to be looking for maxes and mins. So we take that, we have f of x equals 3x plus 5 over 4x plus 8. And we can say the derivative, f prime of x, is going to be, I'm not going to work it all through here, I already worked it out. Came up with 4 over 4x plus 8 quantity squared. Okay. And the only 0 there, again, not even a 0, the only critical number is -2. So if we look at it in a little chart, we would have just the 4 over 4x plus 8. This is almost a trivial exercise because you'll see in a moment why. So it shows -3 and 0, different sides of the -2. Given that the denominator is the quantity squared, I have a constant on top and the denominator is always squared, it's always going to produce positives. So there is no local extrema. Step 6, we look for the second derivative of x. So work this out. I also double check my work. If you use something like Wolfram Alpha, which is how I double check my work, you got to be careful on when you're doing your taking the second derivative. Or well, I just took the derivative again, and I'll be honest, I got strangely different results for taking the original function's second derivative versus taking this derivative as the function, taking the derivative of that. So my second derivative, I had negative 32 over 4x plus 8 to the third power. And again, the only value that we could really see that we can explore is this x equals negative 2. And so if we do that, we would have negative 32 over the 4x plus 8 cubed. So in this case, it's not going to be necessarily trivial. We're going to see what happens here. But given that it's a cube down below, not a square, if we try negative 3 and a 0, putting negative 3 in there, that 4 times negative 3 makes it negative 12, plus 8 is negative 4. Cubed is still negative, and then a negative over negative makes it positive. Putting the 0 in there, it's 4 times 0 is 0, plus 8 is positive. Cubing that stays positive down below, but negative on top, so it's negative. So this means that this is concave up, and this is concave down. And I think I'll just finish off by graphing it here. So a couple things we know. At negative 2, we have a vertical asymptote. At, it was at 3/4, so 0.75. We have a horizontal asymptote. Then we had a couple of places at 0.5/8 was a point on the graph. So maybe we should do a blue mark there. 0.5/8, and what was the other one? It was negative 5/3. Okay. So 0.5/8 would be somewhere, it's under the 3/4 mark, so right about there. And then so it was negative 5/3, 0, so that's over here. This tells us quite a bit on the graphing it. I notice that on the left side of that asymptote, it doesn't cross the x-axis, so it must be all up here. And on the right side, it does cross twice. Like that. And that's a good estimation of our curve. Oh, you can't really see it all. There we go. Okay, hope that helps there. Okay, moving on to our fifth example. 5th of 1,000, by the way. That's what it feels like for this section. Okay, sketching a rational function with an oblique asymptote. So this is going to be fun because we're going to do an oblique asymptote for a change. This is the problem I affectionately call example 5. So, step 1, we have a domain. The denominator x minus 1 equals 0 with look at, so x equals 1 can't be in the domain. So it's going to be negative infinity to 1 and then 1 to infinity. Step 2, we have our intercepts. So the y-intercept occurs whenever x is 0. So f of 0 is going to be 0 squared over 0 minus 1, which is 0. So that means it's 0, 0, it's the intercept. And the x-intercept, occurs when y is 0. So x squared is 0 whenever x is 0. So again, 0, 0. That's our only intercept for this one. Step 3, end behavior. And this is where we deal with that oblique asymptote. Since the power on top is more than the power below, so this is an x squared versus a linear, we would divide. So let's do the division here. X minus 1 goes into x squared plus 0x plus 0. So x times what is x squared? That's an x. So x squared minus x. We subtract, and I get an x out of that. So x times what is x? It's going to be a 1. So we have x minus 1. I get a 1 out of that. I think I wrote my example down wrong or something, but it's a little bit different than what I originally had, but it's close enough. It's so our result is y equals x plus 1 plus 1 divided by x minus 1. Okay. So that this essentially, as x gets really big, scroll over here, the limit as x goes to plus or minus infinity, this of f of x, it'll look like x plus 1. Okay. So let's go on to step 4. I guess I could do down below. I can save this space if I need it for step 5. So step 4, we are going to find vertical asymptotes, and I think we already see where there's a vertical asymptote. Where x minus 1 equals 0, so x equals 1. So if we take a look at the limit as x approaches this asymptote from the right side of x over x minus 1, we'll get infinity. If we take a look at the limit as x approaches this asymptote from the left side of x over x minus 1, we will get negative infinity. Okay, let's see, how much space do we have still here? Oh, I've got plenty of space. Oh, this is just, we can do 5 problems. I'm kidding. Step 5, we're going to look for critical numbers. So if our f of x is this x squared over x minus 1, f prime of x, and there are a few steps to this. I mean, that's going to be x minus 1 times x squared minus x squared times 1 over x minus 1 quantity squared. And I ended up getting a, mistake there, 2x. This is the derivative of the first one, or the numerator. Okay, so I ended up getting a 2x squared minus 2x minus x squared over this x minus 1 squared, quantity squared. So the derivative came out to be x squared minus 2x over x minus 1 squared. So we can take that numerator and set it equal to 0. That's going to be x times x minus 2 equals 0. So x equals 0 and x equals 2 are critical numbers. And we also have that x equals 1 to explore. So I'll do that here. Make a little chart. So we have 0, 1, and 2. And we'll look for a test value. My factors are going to be x, x minus 2, and x minus 1 squared. I'll do negative 1, negative 1/2, positive 1/2, and 3. Putting negative 1 in here, it's going to be negative, a negative, and then anything that's going to go on this bottom one is going to square out to be positive. So we could just do positive across the board there. Put a negative 1/2 in this first one, we get a negative, negative 1/2 in the second one, negative. And it should be a positive 1/2, and this should be a 3/2. So this should be a positive here. There we go. So that's positive there, that's negative there. And then this 3/2 is positive here, still negative here. So that's still negative. And then put the 3 in, positive, positive, positive. So that's all positive. So this means we're increasing, decreasing, decreasing, increasing. So we have a relative, or should I say local max. And here we have a local minimum. So that f of 0 is a local max. And f of 0 is what? 0. And that was also our intercept, wasn't it? F of 2, which equals 4, is a local min. No, that doesn't make sense. I guess this is local min, okay. Okay, so we have one more step before we graph. Let's go ahead and do that. Step 6. Looking for the second derivative. I spent a lot of time on the second derivative, so I guess I can do it. I know that this is already getting long. This is going to be an over an hour long video because I still have more parts to do, more examples to do. So this would be x minus 1 squared times 2x minus 2 minus x squared minus 2x times 2 times x minus 1 minus 1, or times 1, that's times 1, all over x minus 1 to the 4th. And the goal is if we can factor out an x minus 1, that would say, we can knock that down to an x minus 1 cubed down below. So this is going to give us, and we actually do that, an x minus 1 times an x minus 1 times a 2x minus 2 minus the x squared minus 2x, and we have that 2 there, times 2 times x minus 1 over x minus 1 to the 4th power. And so I will divide out here and here, and makes this a cubic instead of a quartic. And what do I have next? Okay, if I multiply through, I'm going to end up with a 2x squared minus 2x minus 2x plus 2 minus 2x squared plus 4x all over x minus 1 cubed. And here's the fun part. The 2x squared and the minus 2x squared go away. The 4x and the 2 minus 2x's go away. It leaves us with a really nicely condensed second derivative of 2 over x minus 1 cubed. And that makes any future derivatives, actually, if you needed to go to the third derivative, makes it really nice. Okay, so what do we get from this? Only thing we have is x minus 1 equals 0, so x equals 1. And so there are no other zeros to look at here. And so if we did a little chart, really little chart, and we have just 2 over x minus 1 cubed, and 1's our critical value, and do like 0 and 2, you'll end up with a negative 1 cubed is negative, so negative there, and then 2 minus 1 is 1, and 1 cubed is positive. So this is concave down. This is concave up. Okay, now it's time to graph it. Let's call this negative 1, negative infinity to 1, and 1 to infinity. So in graphing this, still got a lot of space there, so let's do graph it right here. We had I think the 1 point, wasn't it? We have some asymptotes. So 1 was the x plus 1 asymptote, so it goes up like this through 1. So we're going to call this 1 over here. There's an asymptote here. And it went through 0, 0. Only place it goes through, so in this part, must be approaching that, coming down. And then the upper part is up here. And we know it goes through 2, 4. So it comes down, goes through that, and goes back up. So it does make sense. It's a local minimum, even though it's way above that local maximum. It's kind of funny. Okay, we've got a few more examples still. So let's keep on rolling. Okay, find the oblique asymptote. This one's a nice short problem by comparison. And this is just a division. So maybe you did this in your pre-calculus days, maybe not, or maybe you forgot. So all this is long division. So 2x squared minus 4 goes into 3x cubed minus 2x plus 1. So 2x squared times what is 3x cubed? And this is the hardest part of this one, is that you have to do it with fractions. And that's going to end up being a 3/2 x. So you have 3/2 x times 2x squared. And that's going to become 3x cubed. 3/2 x times 4 becomes a minus 6x. And we're subtracting here. We end up with a 4x plus 1. And 2x squared times what is 4x? Oh, nothing. You know what I did? I forgot to put the 0x squared in there, but it didn't make a difference in this case, because nothing would have multiplied into that. So I guess I got lucky. And I wonder how many of you were screaming at the screen saying, no, you made a mistake. And I did, but it's one of those times when the mistake didn't hurt me. So it's 3/2 x plus, I guess we just say 0 then. So it's going to be 4x plus 1 over 2x to the 4th minus 4. And for all intents and purposes, the oblique or slant asymptote is y equals 3/2 x. Okay. 2 more sketching problems to do. And we get to introduce, actually, one more sketching problem than one where we actually just find the cusp. Okay, moving on. Sketching the graph of a function with a cusp. It's an interesting idea, the concept of the cusp. So you can watch a video that they have made for you if you go into the book notes, the online book notes. There's a video link. Okay, so we're doing f of x equals x minus 1 to the 2/3. So I like to write that as, that's also seen as the cube root of x minus 1 squared. And I'll go interchangeably with this just to help me see things. So our step 1, the domain is all reals. There's no values that's going to make anything not work, because you can have a negative under the radical with a cube or any odd index. So it's all good there. Step 2, the y-intercept is at f of 0. So that's going to be basically the cube root of 0 minus 1 squared. So that's just going to be 1. That's your y-intercept. Our x-intercept is, if we set that, basically the x minus 1 to the 2/3 equal to 0. So then x minus 1 equals 0. You can raise both sides to the power of 3/2. It cancels that out. So x equals 1. So at 1, 0 is your x-intercept. Okay, step 3 is the end behavior. And because it's squared, we don't have to worry about doing a left and right because it squares into negative. So the limit as x goes to positive or negative infinity of the x minus 1 to the 2/3, excuse me, is going to be infinity. Step 4, vertical asymptotes. There are none. No denominator to worry about. Step 5. We're looking for critical numbers. So we take that first derivative, and that's going to be 2/3 times x minus 1 to the 1/3, negative 1/3 power, which is 2/3 times the cube root of x minus 1. So if we look at x minus 1, set it equal to 0, x equals 1. So that's where the denominator is 0, so that's a critical number. Okay, so we can go do a little chart. Very little chart, don't need that much. So we said it was 1, so we can go 0 and 2. And it's just going to be that 2/3 times the cube root of x minus 1. If you put a 0 in there, x minus 0 is, 0 minus 1, I don't know what I'm thinking, is negative, and then negative carries through with the on the cube root. So that's negative. Put the 2 in there. 2 minus 1 is 1. Do all that stuff. That's positive. So that means it's going down then up. So we have a local minimum at x equals 1. And f of 1 is going to be 0. So one thing to point out, I mean, if we look at this limit, this is kind of a special case, and we're going to see in the next problem too. Limit as x approaches 1 from the right of this 2/3 times the cube root of x minus 1. That's going to be infinity. The limit as x approaches 1 from the left of 2/3 times the cube root of x minus 1. Now we're talking, these are the slopes of the function itself. So you see the graph, don't be confused between the slopes and the actual graph. The slope, as you approach 1 from the left, is infinity. The slope as you approach 1 from the right is negative infinity. So that's why it's called a cusp, is because the slopes are not lining up. They go to the same point, but they're not lining up. Okay, step 6. Take the second derivative. We're going to end up with 2/3 times the negative 1/3, which is the current power, times the x minus 1 to the negative 4/3. So you can see that as negative 2/9 times x minus 1 to the negative 4/3. Okay, so this would be, this is defined everywhere except negative x equals 1. Everywhere is one word. So if we make a little chart, so call this 1, go 0 and 2, and it's just going to be that negative 2/9, I need more space than that, negative 2/9 times x minus 1 to the negative 4/3. Putting a 0 in there, 0 minus 1 is going to be negative 1, but in its cube root that carries through the negative. However, it's to the 4th power, so that gets rid of that negative, and then the negative out front for the 2/9 is there, so boom, the negative is still there. Put a 2 in there, it's positive from the stuff inside the parentheses and the power, but the negative is still there. So it is concave down the whole time. Okay. So let's go ahead and draw this graph. And here's 1. And the way this cusp works, so recall that this slope coming down to this point becomes pretty darn steep towards infinite. The slope coming from this way becomes steep but negative infinity. And that's your cusp right there. So they're going to the same place, but the slopes are different. Okay, that's it. Moving on. Consider the function f of x equals 5 minus x to the 2/3. Determine the point on the graph where the cusp is located. Determine the end behavior of f. Okay, so our f prime is going to be negative 2/3 x to the negative 1/3. So that 5 goes away in the derivative. So x equals 0, because that'd be in the denominator. That's like saying negative 2 over 3x to the 1/3. X equals 0 is where this cusp will have to be located, because it's the only place where there is a critical number. So if we look at f of 0, that's going to be at 0, 5. Now let's take a look at the limit. The limit as x approaches 0 from the right side of the derivative, negative 2, wait, do we want the derivative or the original? It's derivative. Negative 2/3 x to the negative 1/3. That's going to be infinity. And the limit as x approaches 0 from the left side of negative 2/3 x to the negative 1/3, that's going to be negative infinity. I had these backwards. The first one was a negative infinity. Second one, because it's a negative infinity going in there, it's coming from that other side, that's going to be a positive infinity. Okay. And then our limit, as x approaches plus or minus infinity, of the original function, 5 minus x to the 2/3, that's going to be negative infinity, because we're subtracting, basically it's something minus the infinity. That's it. Okay, this was quite the section to cover. Okay, it's done. Good luck with everything.